So about 15 years ago, folks in the strongly correlated electron gas community wondered whether you can have analogous type systems in the context of electrons. And in fact, they calculated that indeed you can have something intermediate between the Fermi gases or Fermi liquids and the mod insulators and Wigner crystals. Namely, you can have oriented conduction of electrons in what's called an electron nematic, or you can have even stripy phases or smectics of electron conduction. These are symmetry breakings of the Fermi surface of the electron gas, and in some sense go beyond Fermi liquid theory. So that was thought to be a nice academic exercise in the mid to late 90s. But then signatures of these phases have popped up in more or less all the most interesting strongly correlated electron systems to date. So in Hall systems, in chiral superconductors and rutheniates, in high temperature cuprate superconductors, and high temperature iron-based superconductors. So wow, that seems like there's something really interesting going on. Why do these liquid crystal states seem to always exist in these strongly correlated electron systems? And it gets even more interesting to know where they do that in the phase diagram. So here's kind of a canonical diagram for a cuprate superconductor. You have a strange metal up here, which is strange, and not quite Fermi liquid behavior. And then you have the pseudo-gap regime. And in this behavior, many experiments, say STM experiments, show that you get Z2 symmetry breaking in the conduction of the electrons on top of the point group of the underlying lattice structure. And that is indicative of an electron nematic that other experiments show can fluctuate in micron length scales. So its relationship to the nearby superconducting, D-wave superconducting dome is unknown, whether it is imperative to have that nearby to generate this pairing, it's completely irrelevant, or it actually promotes it. So that's kind of one of the largest questions in strongly correlated electron systems. Well, A, how to promote the temperature of this, but what function do these nematics play? Moreover, in a somewhat analogous, somewhat very not analogous system, another high temperature nictide superconductor, you also see these electron nematics right before there's a structural transition. So it seems like a general concept and warrants further investigation. So, and then in the broader context of soft matter, you also can think about quantum versions of glass. So glass in the classical world is completely poorly understood. No one really even has a consistent definition of a glass through all situations. It gets even worse when you start accounting for quantum fluctuations. So one might want to understand, not just in the classical realm, but even in the quantum realm, what would happen if you had various types of soft matter that's superfluid, okay, in glass. So we'll try to address many of these things in my research that I'll briefly touch on during this talk. So there's two techniques actually three, but I'm just going to talk about two techniques today that we're using to explore this spectrum of physics. And all of them, what we're trying to do is to add new types of components to ultracold AMO that can generate these soft matter. One is interaction competition, which you can do through the large dipolar interaction and spin of dysprosium. Second, continuous symmetry breaking, which we can do through multimode cavity QED. And three, frustration, which we can do with this in internal state dynamics. Okay, so let me begin with the latter point, the cavity QED. So there's an elephant in the room. And that elephant in the room of AMO physics is that there is no crystallization. Might be shocking to some who are not in the field, but only know of the field through nature and science reviews, where they say that we have light crystals, and crystals of lights, crystals of atoms, and things like that. But they are not crystals. So we do not have crystals. Crystals are something that are not optical lattices. Optical lattices have no lattice dynamics. They are imposed by a graduate student with a laser and a mirror, and they retroreflect that laser. And there's no back reaction of the confined particles onto the confinement. And that's something very distinct in all ways from what you actually have in matter. It's something that I'm really pressing on the community to recognize. Okay? So, for instance, this optical lattice, it kind of looks like a real condensed system, like you have with electrons and ions here. They have periodic modulation, but they're very different in all other ways in terms of the essential spectrum of fluctuations. Okay, so the electrons and the ions here conspire to break a translational symmetry. When you break a continuous symmetry, you get what's called Goldstone modes. And in the context of of this system, translational Goldstone moment, because what's called a phonon. Okay? And those phonons can interact with the other dynamics of the system and give you some very bizarre states of matter that are completely absent in everything that we have today. Okay? So, gee, seems like something we need to plug in terms of capability in atomic physics. And that's what I've, for the last 5 years, been set out to try to solve through wonderful collaborations with condensed matter theorists. So let me begin by showing how we think we can solve this. Let's step back and enter the world of cavity QED. So normally in cavity QED, traditionally we focus on single atoms, single photons, that strong interactions, so quantum fluctuations can dominate on the single quantum level. Maybe for quantum information processing, maybe for quantum trajectory theory. But here I want to go to the opposite regime where we have many atoms, maybe a Bose-Einstein condensate. First, let's confine it in a far-off resonant optical trap, off-resonant from this two-level system, but not so far-off resonant from two mirrors that define a cavity mode. And because of the enhanced vacuum energy density of states, you get some stimulated Rayleigh scattering into that cavity that's coherent. Now, initially, the positions of those atoms are in a random way. Okay, so it means that on average you have one atom per anthinode. So if adjacent atoms scatter a photon into that cavity mode, they are pi out of phase and destructively interfere. So in principle, you have no light scattered into the cavity. Now we know that a thermal gas or even a coherent gas will have square root n, let's say, or larger fluctuations in position. So every once in a while, you have more atoms in the even anthinodes versus the odd anthinodes, and that gives you a weak transverse lattice. Now it turns out that if you increase that power up to a certain threshold, then you can get superradiance into the cavity, where the atoms move to either the even checkerboard or the odd checkerboard pattern here. And then the atoms emit in phase into the cavity mode, further deepening this optical lattice pattern. And you get an optical lattice that is not lambda over 2 periodic, but rather lambda periodic, which of course breaks a Z2 Ising-like symmetry between the even and the odd checkerboards. So that was called self-organization by Helmut Rich and Vladimir Voltich about 10 years ago. And ever since those papers came out, I've been thinking about this and wondering what the heck does this mean from a many-body perspective. And over the years, through my postdoc and initial faculty, I've come to refine my notion of what is going on here. So let me explain that kind of trajectory. So one concept that you may first say is, okay, well, what happens if you put a BEC or thermal gas into one of these cavities? Well, whether it's a BEC or a condensate, you'll still get this Bragg lattice that gives you the superradiance. And that was recognized 10 years ago, and then about 5 years ago or so, in the case of a condensate, that you get self-organization. And this was actually observed in the thermal gas. So about 4 years ago or so, we predicted that if you do this with a BEC, you would find that this would be a supersolid, but it's a supersolid that I'm very cautious about calling as a supersolid because it has no Goldstone modes. It breaks a discrete symmetry between the red and the black checkerboards, which doesn't give you any phonons. Okay, so it's only a solid in sort of a notional sense. It's more akin to annealing. And so this is what I call a lattice or point group supersolid, and it's not, I would consider a true supersolid. But nonetheless, you can call it that. And it was actually seen in a beautiful experiment by Tillman and Esslinger in 2010, where you have the condensate and then you have these Bragg scatter satellites concomitantly. So that's a beautiful demonstration. But what this showed us is that a BEC is not enough. It's still mean field. The underlying theory of this is a mean field type phase transition with infinite range interactions because the cavity mediates an interaction no matter how far or close the atoms are together. And then more recently, folks here at Harvard and Cambridge have shown that, rigorously shown that fluctuations are not dominant. It's described by classical equations of motion. It's a classical phase transition, even though some people like to call it a quantum Dicke transition. It's not really essentially quantum. So you can't really, just adding a BEC to this cavity is not enough, but you can still explore many interesting physics like mode softening and criticality, and Tillman and Esslinger has done some beautiful follow-up experiments in that regard. But what other essential ingredients do you need to push this to an interesting quantum phase transition realm? Well, you need a multimode cavity, and here's why. So you need to actually break a continuous symmetry breaking. So you need continuous symmetry to be broken. With the single mode cavity, you have one U1 symmetry of the phase of that mode with respect to the pump field, and you have the Z2, which gives you just a Z2 symmetry, eventually looking at the checkerboard phase of black or red. If you put a BEC in there, you have another gauge symmetry. Whereas if you have truly a multimode cavity, like a concentric cavity or a confocal cavity, you may have thousands of modes, tens of thousands of modes. So you have generally UN-1 symmetries of phases between each of those modes that the atoms then lock when they self-organize. Okay? So to the extent that N is very, very large, this becomes a quasi-continuous symmetry, which should result in Goldstone modes, and we'll show you how that can work in a minute. So just for notational description, the TEM modes we can denote with an L and an M or an N and an M, depending on your preference. And those basically tell you where the zeros in the field intensity are, transverse or longitudinally. So you may start to have the hunch that this will lead to some interesting behavior. And if you start to look about how checkerboards may be formed in a multimode cavity. So let's just take a concentric cavity initially and take two pairs of atoms on the left-hand side. They might say, hey, we like the checkerboard of the 1-0 mode. So let's self-organize into the black checkerboard of the 1-0. But these two atoms over here say, hey, no, I don't really like the 1-0. I actually want to exchange photons and have an effective interaction via the 5-10. And they can do that just the same as these can do that because it's a degenerate cavity and all those energies of those photon modes are the same, even though the spatial patterns are mutually incommensurate in general. Okay? But then you can see that something weird might happen, that this guy's not monogamous and might say, hey, I actually like the 16-3 with you. Okay, so what happens? This is kind of the sense of weirdness that I began with at Illinois and talking with Paul Goldbart and his student, Paul Christian, who's actually in the audience here, and trying to understand what would happen to possible domains or checkerboard formations when you have a multimode cavity. So one intuition that we had over the course in 2008, coming up with the theory of this, is that you can go from long range or infinite range potentials in a single mode cavity, where basically there's just a single mode. So for the perspective of any given atom, anytime another atom is sitting at the potential well here, it can interact whether it's next door or all the way over there, to a multimode cavity where because they're mutually incommensurate, they can destructively interfere to give you effective short-range interaction. But the number of modes that are populated with photons is a dynamic quantity that the lattice emerges through the mutual interactions of all the photons in the pump field and then back reaction from the populated cavity modes back onto the atomic positions and so forth. So it's a highly emergent phenomena where the range of that interaction is it dynamically emerges. Okay, so this is a fully emergent, lattice like you would have in a crystal, in which, to the extent that you have a large number of modes in your cavity, it breaks continuous symmetries.
So just a technical question. So when they say that phonons are Goldstone particles for the translation, you mean low energy phonons, right?
Yeah.
Just in the limit of long wavelengths. Right? Okay.
I'll give you some intuition about what I mean by that.
Okay.
Can I? Maybe this is coming up anyway, in which case you shut me up. But like, how do I construct a dimensionless number which tells me how many modes I need compared to, say, atom number or lambda or size of the cavity? Is it coming up? Or?
It's actually excluded because it gets very ugly. But
there is a way.
There is a way to do that exactly.
To find something that's dimensionless, it tells me this is bigger than 1, then I have enough modes to call it continuous.
Yeah, it's something that you say as it gets larger, you have a separation in the threshold from mean field to a fluctuation-induced larger than mean field number. So the more modes you add, the larger that becomes, and so depending on what experimental noise you have, that needs to be larger than some amount to be able to distinguish it from the mean field case. I'll get to that. Okay. That's a good question. Okay, so how do we treat this mathematically? So you can start with where you'd start as a quantum optician and write down the Tavis-Cummings model, but with all the modes included. So this is the full kind of minimal model for this sort of system. I distinguish it. It is not the Dickey model, which is an approximation to all this. We do not use that. We have to use the full model to account for all the fluctuations in the system. If you do not, you will not get the right answer. So then we start with the task coming with multiple modes. Treat in Keldysh formalism, so convert this into path integral formalism. Treat it in the Keldysh formalism in principle, although we found that you can use an effective theory. And so that you account for the fact this is a non-equilibrium system. Energy goes into the cavity, energy leaks out of the cavity. Integrate out the atomic state, excited state, integrate out the cavity photons, and then you arrive at free energy or action for the system, for which you can start to ask what are the renormalized, what do fluctuations in a renormalized sense do to the various terms in the action. Okay. So the full gory picture of this takes up many, many pages. It was introduced in this Nature Physics paper by Serang, who's in the audience, and Paul Gobart and myself. And then we followed up with an even gorier version in PRA, and all those details and expressions that you seek are in there. Okay, so the upshot of all of that sophisticated field theory comes into, at least from my standpoint, sophisticated field theory, comes into this expression here, which is an effective action. And what's salient about it is that you can show that there is no cubic term. So the symmetry of this quadratic and fourth order action should give you a second order phase transition. But the fluctuations in the system are so strong that, as shown by Brazovskii in the mid-70s in the context of soft matter, you actually kind of renormalize the parameters here. And the control parameter, it gets this extra term, which is kind of like a quasi-momentum in a finite momentum space, in a finite momentum from zero. So what does that look like? So these are the n's and the m's of the TEM00 modes, and if they're at some finite k vector in this quasi-momentum space, given by the size of the cavity, the radius of curvature of the cavity, and the wavelength of light, then you have this control parameter here can go to 0. And so what this gives you in the classical world, in polymers, are stripes at this kind of length scale that wander around into pi, okay, given by maybe this is kx and ky. Here it's m and n of the mode indices. But you see that it's the same wavelength, but you have this stripy business with topological defects between them. You could also see this in Rayleigh-Benard convection.
So what is the order parameter here that shows the first order transition?
Well, I'll get to that in a moment. Okay. I mean, the order parameter here would basically be something that looks like a condensation on a ring. Okay. So, for instance, if you were to do Bragg scattering off of this, and you should be able to see a ring because this is a symmetric, and you'd be able to see a symmetric with scattering parameters. So that can be your order parameter. Okay. So, but basically, it's the order parameters are contained by the condensation of these modes. Okay, so this is in the classical world. And it's an example of a rare example of a fluctuation-induced first-order transition. So basically, instead of it being second order, fluctuations induce it to be first order. And that's a weird thing, and it's not seen very often in nature. So what we did was actually show that there can be a quantum Brazovskii transition, in that instead of a full ring, you actually have a lot of soft modes where the n is large. That's the number of nodes along the longitudinal axis, and then maybe 1,000 or 100 modes transverse to it. So you have these little brackets here instead of a full circle, but nevertheless, that's enough to give you a Brazovskii transition where you have excitations around there like so. Okay. And so it drives this transition from second order to weakly first order, where at mean field, you would expect it to have this nice kind of second order transition, the fluctuations bend it over again, like so. Okay, and so the soft mode in the system, you can see spectroscopically by saying that, okay, let's look at how this mode starts to soften. And if you had a single mode case where if you wanted to, you can treat it in the Dickey way, or you can use Tavis-Cummings, you would see that it would go down to 0 smoothly, whereas in the Brazovskii transition, it's discontinuous. It's a weakly first order transition. You should see fluctuations at a laser strength characteristic of this difference for an amount that is dependent on the number of modes in the cavity. Okay. So various detection schemes are, you could look at the spectrum of those fluctuations coming out of the cavity. You can do it spatially as well, because it will happen differently for lower order versus higher order modes potentially. Correlation functions of the light coming out gives you the moments of this free energy spectrum, the first and second order curvatures. And then by changing the mirror position, which you can do in situ with piezos, you can kind of topologically deform the phase portrait from the single mode case, which is well known to be all second order transitions from the superfluid to the quote unquote supersolid to something that's like a Mott insulator, to the Brazovskii case in the multimode portrait, where this changes into a weakly first order transition to a supersmectic, which I'll describe why it's a supersmectic in a moment, to then to the solid, or maybe even as a function of short range scattering into first order into solid. And of course, you can do Bragg scattering and look at the analogs of what you would see for normal liquid crystals. Or you could start. Okay, so extensions so that shows you that in principle one should be able to see something that looks like supersmectics inside the system. So you should see some ordering where you have some topological defects that are reminiscent of splay modes and various types of defects that you see in a supersmectic. But if you put many layers together, my battery's dying here. If you put many layers here of the BEC transverse to a certain plane, then you start to generate something that's like frustration. Because if you try to organize in a checkerboard of the TM16 in this domain, you're going to have trouble doing it in the TM26. Now, the phonon fluctuations will be in small variations of these indices from like 6 to 7 and so forth. So that gives you this smooth ability to deform into various different modes. That's where the rigidity comes from. But generally, if you organize into a particular pattern here, you'll be frustrated in your organization up in a different plane because the odd modes change sign in terms of the checkerboard, whereas the even modes do not, and then you don't know how to organize any longer. So you have the phonon dynamics, because you have maybe 1,000 different modes that these guys can locally have little droplets of organization into. It's a supersmectic on large scales because the order parameter is consistent with the defects associated with the wandering smectic. On a small scale, it is a true supersolid because it broke that continuous symmetry. And in many layers, it becomes what we call a superglass in this context, because the more and more layers you put in, the more geometrical frustration you have, the less long-range order you may have. And this is very akin to what you have maybe in a normal glass, where you have no long-range order, but you have order in time, in the sense that if you poke it, it'll take a long time to relax and may never reach equilibrium, or equilibrium is not even well defined. And if you cycle it through many times, you will get different memory effects. In the quantum realm, this has been explicated in context of helium by Nicolai and his collaborators in several publications. Okay, so there's another way in which you might be able to see quantum soft matter with the cavity, and that is by fixing the positions of the atoms, but imbuing them with a pseudo-spin 1/2 by a lambda transition. So if you have a pump laser on one leg of the lambda transition, and then use the cavity on another with the Raman transition a little bit off resonance, then in a time scale of 1 over delta, you can have a virtual spin-spin interaction between two remote particles, or one spin flips, the other one spin flips, exchanging that virtual photon before they go back again and then scatter into the cavity mode and out of the cavity. And so that virtual interaction can give you either a ferromagnetic or anti-ferromagnetic interaction, depending on whether the atoms are a multiple of lambda from one another or a multiple of lambda over 2. Because if they're lambda, they have, say, 0 phase difference. If they're lambda over 2, they get a pi phase difference, and that changes the sign of the J coupling, the Jij coupling constant from positive to negative. So in kind of a 2D plane, this means that depending on whether they're lambda or lambda over 2 from one another, from the perspective of any given spin, you can have a kind of a summation over ferromagnetic and anti-ferromagnetic interactions with every other spin, because the cavity mediates infinite range interactions in the single mode case. And of course, in the multi-mode case, the more layers you put on, each other mode will have, in some sense, a randomly distributed number of nodes and antinodes between any given spin. So superimposed on some ferromagnetic interaction will be an anti-ferromagnetic interaction. Whereas this gives you some random like IC model, or more specifically a Mattis model. This, in the limit of many, many modes, starts giving you frustration. So with the initial disordered positions, the frustration gives you a glassy state. So in other words, this realizes this Hamiltonian here. So this is the atomic physics version of this Hamiltonian like that I've written right here with the spin-spin interaction, this is directly transformable to the canonical Edwards-Anderson model of spin glasses. And in the limit of multiple modes, you get the glass. To be more specific, what we showed in our paper in PRL and a follow-up later on is that you can tune between very interesting degrees, interesting phases. So as a function of temperature, you have this paramagnet. That's nothing much is happening. If you lower the characteristic energy scale and you have few modes per atom, so you have a single mode cavity or close to a single mode cavity per atoms, down here you have what's called a Hopfield associative memory. It's a very reduced model of a neural network. And then as you increase the number of modes per atoms, you, in the limit that you still have just a few number of modes, you have what's called an infinite range Sherrington-Kirkpatrick model, which ostensibly has been solved in what's known as replica symmetry breaking formalism. It's a mean field type model. But then most interestingly, if you keep pushing the number of modes per atom, you should enter a short range Edwards-Anderson model, for which there's no universally agreed upon microscopic model or notion of what happens there, even though this is where real spin glasses and materials lie in short range interactions like a RKKY interaction. So more specifically, there's a conflict in the community over the last 30 years between whether in this limit here you have infinity of order parameters in a free energy landscape that looks like this, versus a droplet model where you have generalized spin up and spin down and you only have 2 order parameters. And the groups of people who adhere to these really dislike each other and have been warring for 30 years. And at least Phil Anderson considers this problem to be one of the largest unanswered question and the greatest unanswered question in dense matter physics, even more so than high temperature superconductivity. So, which I found that surprising as a quote from Phil Anderson. But this thing we might be able to resolve in our system because we can tune between these two regimes. In this regime, it's mostly resolved that it should be this picture in the replica symmetry breaking. But in this regime, no one has access to controlled experiments. Numerics fail in that regime. Lastly, we can maybe turn this into not a quantum computational device, but a very interesting and efficient classical computation device by working in this regime here and noting the analogy between this and neural networks. And so we're exploring how to do message passing and decoding in this type of system. Okay, so let me just remark that my collaborators, Sarang and Paul Gobart, have noted that there's a quantum version of this. And here at Harvard, Sabir Sachev's group has also done some great work in this regard, in showing that you have quantum spin glasses and itinerant and metallic Fermi glasses if you were to do this with fermions. So there's a lot of great work that's being done on this right now. This came out this year and last year. Okay, so in our lab, we've built the apparatus. We have nearly a BEC. Our cavity system is completely tested, and we're ready to put the condensates into these multimode cavities. Okay, so in the few remaining moments I have, let me move on to the other way in which we're striving to make quantum soft matter. And this is with ultracold dysprosium through interaction competition in large spins. So, so the notion is that magnetic dipoles can actually give you spontaneous symmetry breaking of the Fermi surface, in the sense that you can get Pomeranchuk instabilities of the Fermi surface, either in a spin polarized sense or in, say, coupled to a Stoner instability. And that is something that's qualitatively very, very new. It's hard to see in any condensed matter context. So I think the first theory on looking at these pneumatics, true pneumatics in dipolar atomic systems was done in collaboration with Eduardo Fradkin while I was at Illinois, and followed up by looking at these ferropneumatics. And since then, there's been a tremendous outpouring of wonderful papers showing all the different variety of phenomena that can arise from Pomeranchuk instabilities coupled to spinors in these dipolar systems. So one in particular is a neat state that is antiferromagnetic smectic C phase that it has analogies to meson condensation in neutron stars, which is actually where quantum liquid crystals were born 20 years ago, and thinking about spaghetti states of neutron stars. So now we've come full circle and back to thinking about analogs of those. And you can start to build a picture of these quantum liquid crystal states as a function of S-wave scattering length and dipolar length, where you have these smectics, ferropneumatics, and the normal just Fermi gas here. And with dysprosium, we should be able to access this regime here and this terra incognita over here. So in principle, we should be able to explore some nice physics with this. But more importantly, we should be able to look at the quantum melting of a nematic to a smectic, which is in some sense what's going on with these Cooper superconductors and Nictide superconductors, where the smectic doesn't actually appear because it's taken over by the D-wave superfluidity, ostensibly. I mean, there might be a quantum theoretical point there. So we can explore this without lattice or tunability complications. The challenge is that magnetic dipoles are weak, but we can't use electric dipoles because there are no such things as permanent electric dipoles. They have to exist only in the presence of a symmetry-breaking electric field that mixes opposite parity states. So we have to use magnetic dipoles because they exist even in the absence of a magnetic field. But that also means that we don't have to worry about chemistry, and we have them for long lifetimes, okay? Which may not be true for a polar molecule, a diatomic magnetic molecule, but certainly just for dysprosium by itself we can do. Okay, so I'll be as quick as I possibly can. So dysprosium is the most magnetic element, and certainly that's true for the fermions. As the bosonic isotopes, it's tied with terbium, which has actually never been laser cooled, but terbium has no fermionic isotopes, so that's why we're focusing on dysprosium. I'll just breeze through this. It's 200 times more energetic in the dipolar sector than rubidium, around 10 more than chromium, twice as erbium, about the same as KRB if we use a shorter wavelength lattice. Were you to make dysprosium 2, you could get up to large dipole moments, but as we've seen, lifetime issues are extreme. So we have 3 bosons that are I = 0, 2 that are 5 halves. It's a very complex energy level diagram. I think it has the most number of states of any of the lanthanides. And the fermions have even more structure. Nevertheless, we can know how to make a mod out of this following the groundbreaking work in erbium by Jabez McClellan at NIST. And okay, so no one had ever laser cooled dysprosium, but we did. We trapped it, and these are many publications that show you all the technical details, and I'd love to tell you about that later, but I'm going to skip all that. Just show that we have 3 lasers, a very wide transition here that we had to find. So the spectroscopy is actually, from an atomic physicist, pretty lousy. And none of these, very few of these line widths are known to any accuracy or positions. We had to find this line, which turned out to be only 2 kilohertz wide, and then here's the ODT. That's what it looks like. So we were able, to, however, despite all those challenges, to make a dysprosium BC. Here it is. We can actually do it of other isotopes as well. We can show that it has these D-wave collapses without having a Feshbach resonance in play, or at least if you go to a low-field Feshbach resonance, you can get the D-wave collapse. If you go away from this sort of business and just tilt the magnetic field with respect to the axis of symmetry, then you can see that the condensate collapses without a Feshbach resonance around, so it's natively strongly dipolar. You can even see that the expansion rotates due to magnetostriction, and that's been qualitatively reproduced by Ryan Wilson for large dipole versus contact strengths. We made the first dipolar degenerate Fermi gas, where the dipole energy was non-trivial, showing that we can get down to 0.2 T over TF, which means that the dipolar versus Fermi energy is still perturbative, but nonetheless it actually matters in the sense that we can evaporatively cool identical fermions to below T over TF. And that's the first time it's ever done before. That's because this large dipole moment changes the Wigner threshold law for scattering lengths to something that's finite. So this is proof positive that we have non-trivially dipolar fermions and that we've seen universal dipolar scattering. There's a very strong signature of universal dipolar scattering. Lastly, I'd like to extend the talk of Jason Ho's yesterday. So they had this wonderful description of the exotic spinors and topological matter that can occur with large spin states. So you can classify these using Majorana representations. The topological defects of these should be exotic because a lot of these symmetries are non-abelian, and that's something that we can explore and play with in a way that only can be speculated about in QCD, where these things first were thought about. And then more recently, we have done a theory collaboration together to ask what happens if you couple the whole manifold of the states with 2-photon Raman transitions. What we found is that you can have these oscillate in space in something that we call a Majorana spinor helix. So these things kind of oscillate in space, kind of like a persistent spin 1/2. state helices that people see in quantum wells. We can do this with a very large spinner and build up a very exotic phase diagram of all these different states controlled by this Raman coupling. Lastly, we can get, from day one, a 10 times larger synthetic gauge field, which would bring us closer to quantum Hall effects. And I'm happy to note that our paper appeared on the archive today. So it's fresh, it's on the archive, and maybe you'll enjoy the read. And, okay. All right, so with that, I'd like to conclude and thank my students, my new postdoc on the Dysprosium experiment, my students now on the cavity QED experiment, and there's a third project that I didn't get to talk about, but I'd love to answer questions about that if you have any offline. And thank my collaborator, Sren Gopalakrishnan, that's up there. All right.
Time for one of the quick questions.
Well, it was very good explanation of why a lattice is not a crystal, etc., etc. But at the end of the day, since you have mirrors, don't you anyway impose a kind of external cavity breaking in contrast to spontaneous symmetry?
That's a great question, and that's exactly why I don't call the single mode case super solid. Because in a single mode case, the symmetry is reduced already from continuous to a point group symmetry, a Z2 symmetry. So that's exactly the right intuition for the single mode case. In the multimode case, to the extent you have thousands of atoms, there are n-1 U1 symmetries between each one of those modes. Each one of those can be broken independently of the other. In that limit, it becomes quasi-continuous. It becomes continuous. And you can show that you get rigidity now in the lattice, where you don't have the rigidity in a single mode case or in an optical lattice.
But did you consider, for instance, when you have a ring cavity, you don't have the same problem, because in a ring cavity, you don't have this imposition of a hard wall somewhere.
So I wish I hadn't skipped that slide, but I have a slide about ring cavities. So Seren found that in a ring cavity, indeed, you do have a Goldstone mode, one Goldstone mode, because you can lock the phase between the counterclockwise and the clockwise mode, but it still reduces to a mean field model. So it doesn't give you anything new.
Okay, thank you.
I'm wondering what the role of the cavity is on a more general level. If you have a large atom number, you could have something like omnidirectional superradiance, which would give you a whole continuum, basically of M&M values. And I guess in your theoretical description, where you sum over M&Ms, now you would basically replace this by an integral. But I don't see what the main qualitative difference would be.
Between what?
Between having no cavity at all and having a cavity with very many modes.
Because each of those modes has a large vacuum Rabi coupling.
But suppose you could increase this coupling through an increase in the optical density. Have some kind of spontaneous superradiant processes in a, let's say, spherically symmetric points.
So, I mean, there's an interesting experiment at Duke, and people have done this 10, 20 years ago, with looking at high optical density vapors and then driving them very strongly. And the difference is that the quantum fluctuation aspect of it, it's very, very suppressed. You don't have a separation in timescales where you can look at fluctuation-dominated transitions before you get to thermal. So it basically reduces to something that's less interesting. I mean, you can have these dynamical Carl or recoil-induced resonance things. Yeah, so you do those in a multimode sense, but it's mathematically distinct from what we're doing.
So I got two questions, but essentially it's the same question, except with different, so to say, applications. So the problem between the Parisi picture of this spin glass being really consisting of many local minima of free energy, and the droplet picture of Hughes and Fisher, in which it's very similar spin glass to an Ising model. The only difference is that the domain walls energies scale differently with the size of the domain walls. This is a classical, so to say, the problem. Okay, but still the question is, how do you see the detection of these differences in the experiment? And the second question is, the same about the quantum spin glass regime of Subir, how will you then see the quantum, so to say, signature?
Okay, so to tackle the first question, so what I suspect you'd want to do, just like you would have with the materials, look at some susceptibility measurements over large variations in trajectories of cycling. So you look at aging effects, you would start with different memory effects, you look at the relaxation over many orders of magnitude time scale. So the first order answer to your question is that you look at the entire system over different cyclings, different agings, and you would first demonstrate that you have glassy behavior as a function of the number of modes that you put in. And we have 5 orders of magnitude of quantum fluctuation dominated, and then about 3 to 4 orders of magnitude after the system heats up from an effective temperature that's proportional to kappa in E recoil. So you have about 7 to 9 orders of magnitude time scale to look at this, which is comparable to other systems. Now, to then distinguish it between, say, a replicable symmetry breaking scenario and a droplet, what you want to do is measure the Edwards-Anderson order parameter, QEA, in some way. And so the way that one might be able to do that is to look at these spins on half the system or a particular part of the system and compare it to another part of the system at different times. So they both have the same quench disorder, but then they could have different. You could treat them as, say, different replicas because they all see the same modes, but they're actually different parts of it. So in some sense, you can have replicas in a way that it's very hard to actually do in any thermodynamic limit in a numerical calculation. And then by looking at the overlap between those as a function of time, you may be able to see something that distinguishes 2 QEAs from an infinite continuum of QEAs. The exact details of how to do that we're thinking about now, and but my sense is that's what you would want to do.
But it's
And in terms of
important, difficult problem.
Yeah, it's one of the greatest unsolved problems, and numerics just can't do it because finite size mimics replica symmetry breaking. The latest simulations by Young, Santa Cruz, start to show that you kill some of the dispersion in the QEAs, so it starts looking like droplets, but it's not fully convincing. So this has many orders of magnitude more particles involved and a large number of decades in time scale. So maybe we can address that problem. And then there's the quantum fluctuation aspect, and Subir's calculated some response functions that change depending on which regime you're on. So. But it could use a lot more theory.